Hello, everyone, and welcome to our new topic in physical chemistry. So we're going to now be starting on our major theme for the rest of the semester, and that's going to be focusing in on the topic of energy. So energy is really important. As we've seen before with gases, it's going to be a very reliable metric of the behavior of a system. And so before we can go ahead and use energy to describe how a system behaves chemically, first we need to actually make sure that we're all on the same page when we talk about energy, because turns out there's very different definitions of energy colloquially in physics, in chemistry, and even in biology and geology. So when we're talking about energy in chemistry, what we're often going to be talking about is thermodynamics. So this is going to be the study of how an energy moves within a system. Say if I have the energy moving in inside a beaker of solution reacting, and also the energy moving between systems. So if I'm heating or cooling a sample. And as we've seen before, how the energy of the system behaves, how the energy of the system is also going to really tell us a lot about the behavior of the system on an atomic level. So how the molecules and the atoms move. And we've already seen this with the kinetic energy of a gas being highly related to temperature. And so what ends up coming out of the study of thermodynamics is that if we really understand how the energy in a system behaves, we can really predict all of the behavior of the system, because all movement and transformations is inherently going to be a thermodynamic process. So thermodynamics might be one of the most fundamental cornerstones of modern chemistry. So before we go ahead and really dive into our study of thermodynamics, let's go ahead and walk through some definitions. So first, we need to actually look about what system we're studying. And it turns out we can divide a lot of our systems into three major categories. So the first one is going to be an open system. So this is your classic beaker of water sitting in an open room, where we can have both energy and matter moving in and out of the system. So it turns out if I'm allowing energy and matter to move in and out of a system, these systems are going to be very tough to study, as some of this matter is also going to be carrying energy, and well, that makes it really hard to keep track of what's happening. So instead, we often prefer to look at closed systems. So this would be, say, looking at how energy flows in and out of, say, a closed pot. So while no water can go ahead and get in and out of a boiling pot as long as I have the lid on, I can still monitor what happens with the energy. And this is going to be highly related to our last system, which is isolated, where no energy or matter can cross any barriers. So isolated systems are often a very good place to start, as all energy is just going to be moving internally inside the system. But if I want to really look at the movement of energy, closed systems can be highly useful. And the hope is that we can use what we learn from closed and isolated systems to really look at open systems. However, we also have a series of definitions to describe these types of boundaries. So again, since we're mostly focusing on energy, let's talk about how energy moves across a boundary. So if I can allow energy to move across a boundary, say in a closed or open system, this is called a diabatic system. So if I go ahead and put a pot of water on a stove, my steel container is going to be diabatic. Energy can move in and out. However, this is contrasted to an isolated system where no energy is allowed to move across any barrier. This is going to be called an adiabatic system, where I'm not going to allow any energy to move in or out. So when I use adiabatic systems, it's often the phrase adiabat. It's often useful to be thinking of an isolated system. However, if I'm talking about a diabat or a diabatic system, this can refer to either an open or closed system depending on the context. So this tells us a lot about how energy and matter moves in and out of a system, which is going to be a good first set of constraints. However, when I say energy, what the heck do I mean? So, when I'm talking about energy, this can have several definitions. However, according to classic thermodynamics, uh, when I'm talking about energy, what I'm explicitly referring to is the maximum amount of energy of work that a system can accomplish. So this is going to be focusing in on specifically what sort of work can I do on my surroundings. And it's important to understand that a lot of our classical thermodynamics was built around the study of things like engines, like the primitive steam engine, because it turns out this was a really important new field of study. So, unfortunately, all I really did here is shift my definition from what is energy to what is work. And so, work is essentially going to be defined as performing motion against an opposing force. So, if I have to apply some amount of energy against an opposing force, that energy is called work. And when I talk about a change in energy in a system, what I'm really looking at is what's the maximum amount of work that it takes to accomplish that sort of change. So let's go ahead and work kind of a specific example. So let's say uh, I have a waterfall. So in this case, I have water flowing over the edge of a cliff. Turns out that this water isn't doing any work because it's not performing, while it may be moving, it's not going against any opposing force. It's just falling freely off of a cliff. So, so no work is being accomplished. However, I could get some work out of the system if I put an opposing force uh, uh, for that water to act against. So, for example, what would happen if I put in a dam across the system? Well, now my water is going to have to perform some work against, say, a turbine to uh, to exit down at the bottom of the cliff. So it turns out in this system, my water's doing no work. In this system, it's accomplishing some work. However, both of these systems can have the same energy. So work is going to depend upon what exact conditions you're operating against. However, energy is focusing in on just if I applied an opposing force, what's the maximum opposing force that I could act against and still have the same change? So this can be a little bit messy, but hopefully as we work more examples throughout the semester, it'll become a little bit more clear. However, there's also other definitions of energy that apply to more kind of modern notations of the study of thermodynamics. So one of the more modern applications of thermodynamics is called statistical mechanics. So in statistical mechanics, one of the important takeaways of energy is going to be telling us how likely something is to occur. And we saw this earlier when we talked about Boltzmann distributions. So in this notation, what we're really looking at is the probability that our system is going to be in some specific state that is going to be defined by the state variables n, v, and t. And it turns out that we can predict the probability of our system being in a single state if I know the energy of that state and I know the sum of the energies of all possible states the system can be in. So if I have a very low energy, this means that this exponent will be closer to 1. If I have a very high energy, this exponent will be a very large negative value, meaning that this state is very unlikely to occur. Similarly, the more states I have, or the more possible configurations my system can adapt, the less likely any given state is to occur. So we're going to be coming back to this idea periodically, but it's really important to note that energy gives us not only this work definition, but also this probability definition. And we've actually seen this definition used in general chemistry with our old friend, the Gibbs free energy, where we have our equilibrium constant, or the probability that our system is going to be in a product state divided by the probability it's going to be in a reactant state, is given by essentially an exponential term of the difference in energies between the two systems. And again, we replace our Boltzmann constant with an ideal gas constant as we go from a molecular base to a molar base. And it turns out that we can actually use some of our lessons from Gibbs free energy for some good general guidelines. For example, when we're looking at Gibbs free energy, it turns out that a 1.36 kcal difference in energy is going to be the same as changing our probability by about an order of magnitude. So when we're looking at energies in terms of a work basis, it's also important to realize what this might mean on a more chemical reaction level. And this can be useful to have in context. So we've been focusing in on these energetic definitions, but it turns out that energy can be split up into different forms. So we're typically define energy as either occurring in a potential form, where it can accomplish some action, or as we've talked about more recently, a kinetic form, where our energy is actually occupied in some active movement. And as we've seen before, we can relate our kinetic energy of our system to the velocity of the system as related by mass. So this is your classical physics definition, where kinetic energy is equal to 1/2 mv squared, or the momentum squared divided by twice the mass. We'll occasionally be using both of these definitions throughout both this semester and next semester, but fairly intermittently for the rest of this semester. However, one of the things that is worth noting is that this movement can be caught up in either straight line directional movement, if I have, say, flowing water moving through a tube, but it can also be caught up in the random movement of molecules. And we've seen this a lot when we're talking about the kinetic gas model, that most of our gas is moving in random different directions, but that doesn't mean it doesn't still have some amount of kinetic energy. And in general, we aren't quite so much interested in samples of liquid, say, flowing through pipes. We tend to leave that more to the chemical engineers. So as a whole, we're going to be generally avoiding bulk directional movement and spending a lot of our time more on this random movement, which, as we've seen, random kinetic movement is often described as temperature. So if I have a mononuclear gas, my energy, kinetic energy in my system can be given as 3/2 kT, or in a per mole basis, 3/2 RT. However, don't forget, if we have a linear gas, it's going to have a kinetic energy of 5/2 RT, and that if I have a nonlinear gas, that's going to be a full 3 RT. So this will help describe how much energy is in the movement of the system. But don't forget, we also have potential energy. So this is going to be the amount of energy that can be turned into some form of movement. So while it's often easy to measure exactly how much a molecule is moving, because I can either say, watch it move across a room, or measure the temperature, potential energy can be a little bit trickier, because we need some relative position. Because what we're often talking about in terms of potential energy is less an absolute value, and more often it's going to be dictated by how much energy is required to return to your starting position. So you're often going to see, when we're talking about potential energy, it put in terms of, say, dV or delta V, as in the difference in potential energies. Now, because we already have too many V variables floating around with velocity and volume, we're often going to use the E subscript P to designate our potential energy. And so in terms of kind of a classical displacement form of potential energy, of energy being stored in the position, we can think of this uh, as how much energy would be required to move my position against some opposing force. So this is classically described with our omnipresent opposing force, gravity. So our potential gravitational energy is going to be dictated by the height of a system. Because if I go ahead and lift a bowling ball, say 1 meter, then I'm going to have to expend some amount of energy to change the potential energy of that bowling ball. And the opposing force I'm acting against is going to be the mass of the bowling ball as acted upon by gravity. So when we're talking about positional energy, this is going to be kind of our go-to, and we'll use this equation on and off. However, you can also imagine this applying to things like electronic forces, where my opposing force is actually going to be more of the Coulombic interactions, or the attraction between two charges, and and the difference I'm acting against is going to be the difference in position. So if I have two similar charges, I'm going to have to put in an opposing force to separate them. And if I have two similar charges, say two negative charges, I have to put in energy to force them closer together. And again, the signs of the charge will help dictate that. And then just like gravity is our medium in which the gravitational constant dictates the medium in which the gravitational force applies, our epsilon here is going to be our vacuum permittivity, or how well charge is transmitted through through vacuum. But again, this can be adjusted if charge is being transmitted through some other medium. But again, when we're talking about potential energy, we're often looking at trying to move our systems against some sort of opposing forces. And it turns out that this can include things like arrangement of the atoms. As I'm making or breaking bonds, I'm really going to be playing around with complex forms of electronic interaction. So it turns out that when I'm talking about the energy of the total energy of my system, I might need a little bit more convenient notation to accommodate both our potential and our kinetic energy. And so when we're going to be talking about the total energy just in a system, we're often going to be using the notation of internal energy. And so we can think of this as the sum of all of our kinetic energy. So this one's going to be fairly easy to measure as we're going to be mostly looking at the movement of the system. Generally, we're going to be ignoring any bulk movement. So our kinetic energy is mostly going to be dominated by thermal contributions. With, again, as a reminder, each direction of movement is going to add a half kT of energy. So if I have a monatomic gas, I only have 3 translational degrees of motion. So that gives me 3/2 kT. If I have a diatomic gas or any linear gas, I'm going to have 3 degrees of translation, 2 degrees of rotation for 5/2 kT. And any non-linear molecule, I have 3 degrees of translation and 3 degrees of rotation for a full 3 kT. And we went ahead and proved this general idea when we talked about the kinetic gas model. And when referencing other notations, it's worth noting that each of these tends to be called a degree of freedom. However, that's just the kinetic energy. And as you may have noticed, being linked to temperature, this one might be a little bit easier to study. But it turns out that we also have to define our potential energy. So our potential energy is what's called a state function, in that it's going to be very uniquely defined by the state of the system, which again, as a reminder, means that if you know all of your state variables, say your temperature, your volume, your number of molecules, and your pressure, along with the identity of your gas, you're going to perfectly know your potential energy. whereas our kinetic energy is mostly going to be defined just uh, by the temperature of the system and the amount of the substance, as we've seen before in the kinetic gas model. However, it is worth noting that we often need to include the volume of our system to help give us some information about intermolecular interactions, such as, say, how tightly packed our system is, especially when we're deviating from ideal behavior, and and the amount of IMF interactions. The importance of intermolecular force interactions is going to start really dominating this potential term. So, in general, if I'm going to define my my total internal energy as a state function, it will be uniquely defined by three of my state variables. And by convention, we typically use N, V, and T. So as long as I know these three state variables, I know the internal energy of my system. Now, next time, we get to start looking at how the internal energy of our system can change and what information this might give about the behavior of a system. Till then, take care.